Thank you for your interest in this video, which will highlight and demonstrate several of the many advanced features of Modelithics models. In this video, we will present the substrate and part value scalability features of Modelithics microwave global models. In showing these features, we will also take advantage of the optimization and tuning compatibility of the models. What are microwave global models? The capacitor icon shown here is one example of a microwave global model as it appears in an electronic design and simulation tool. Note the many unique parameters that are included. The models are measurement-based equivalent circuit models. The measurement validation means that they capture parasitic effects caused by factors such as substrate and pad dimensions. The advanced equivalent circuit model format allows for built-in scalability of these factors, and in turn allows for powerful design and analysis capability. To summarize the parameters seen here, the component part value can be varied within the model. Also, the substrate properties are taken into account and are accurately simulated based on the measurements included in the model. The sim mode parameter offers built-in pad de-embedding, which allows for incorporation of custom pads and is also often used with EM co-simulation designs. The tolerance parameter provides for statistical analysis capability. And seen here, you can scale based on pad dimension. Also, the component orientation can be considered and simulated in certain models. The last parameter shown here is the discrete optimization parameter. This allows for discrete optimization based on part values that are actually available from the vendor. In addition to the many features just summarized, Modelithics models are valuable for even more reasons. They represent commercially available parts from many popular vendors, and are all developed using standardized modeling processes even across vendors. The models incorporate many measurement types to validate and verify accurate simulation. They are compatible with the statistical analysis tools of the simulator, which allows for unique and powerful design analysis techniques to be used. The models are packaged in comprehensive libraries that contain hundreds of models representing thousands of individual parts from many vendors. The vast amount of information contained in these model libraries makes it easy to justify as a huge value over in-house modeling. In this demo, we will show a simple substrate scaling example and will incorporate the tuning tool. Accurate response based on substrate is critical in high-frequency design. Being able to capture substrate-related design issues early on is very valuable. We will then show a part value scaling example. In this example, both tuning and optimization are utilized to show how the component value can be changed and used as a variable to maximize design performance, accuracy, and cost effectiveness. In this substrate scaling example, we are showing a model on the left for a Vishay 0402 capacitor set at 3 picofarads. On the right, we have a measurement file for the same capacitor, and this one particular measurement was done on 6.6 mil Rogers substrate. The substrate definition for the schematic is set at a 30 mil Rogers substrate, so that is what the model will be using initially. Here is the result of the initial simulation. You can see that the red model and the measurement obviously don't line up very much. Now let's tune the substrate. We have the height and dielectric constant set at tuning parameters. As we tune the substrate height lower, down towards the 6.6 mil, you can see the model lining up much better with the measurement. And we really don't have to adjust the dielectric constant too much in this case, since the different thickness of Rogers material have similar dielectric constant. And you can see the S11 and S21 both match very well. Here is a part value scaling example. We have the same Vishay model here, and this time the capacitance is set at 6.2 picofarad, and the substrate being passed into the model is a 6.6 mil Rogers substrate or similar properties. The measurement was taken on 6.6 mil Rogers as well, but this is for a 0.8 picofarad capacitor. So let's just simulate right now and see the difference between the two capacitance values. And you can see they don't line up very much. The red is the model and the blue is the measurement file. So we can try it by tuning first. And we have the capacitance value set up as a tunable parameter in the model. And we know that the measurement is 0.8, so when we go to 0.8, you can see how well the model lines up with the measurement. And we also have an optimization parameter set up to make the difference between these, the S21 in this case, to line up. And it's just going to finish out the iterations. You can see it lines up very well, and in the optimization window we came up with 0.8 picofarads as the optimal value. So you can consider a situation in which you're using multiple Modelithics models throughout your design, and for different components, you'll be able to set the value as a tunable or optimizable parameter and set up multiple optimization goals that represent your overall design goals. And once you run that optimization, you can simultaneously vary the part values for multiple parts at the same time to come up with the optimized design. The scalability and the tuning and optimization examples shown here are really useful for coming up with a good design, an accurate design quickly and easily, and is something that is really not possible with S-parameter files. Thank you very much for watching. The example project used for this video is available for download on the Modelithics website. If you have any questions, please contact Modelithics at support@modelithics.com.